All right, welcome everyone to the second and hopefully last YouTube edition of ITCS. My name's Ian. I'll be talking a little bit today about lifting theorems in communication complexity using the sunflower lemma from combinatorics. So my co-authors on this project are Raghu, Meka, Jiapeng, Zhang, and Shachar, Lovett over in California. And then here on the East Coast, Tony Pitassi, my advisor at University of Toronto, who's currently at Columbia. So today is going to be a story of two computation models, decision tree complexity and communication complexity, one weak model and one strong model. So let me introduce you to them. So decision trees capture the natural notion of adaptive queries. So in an adaptive query model, you want to know the value of your function f on some input z1 up to zn. And the way you're going to do it is you're just going to ask about successive variables. So you might first just ask about the first variable, z1. And then based on the answer you get, you might ask for, say, z3 if you saw a 0 before, and ask for z7 if you saw a 1. And anyway, as you accrue these answers, you keep asking more and more questions. And eventually you say, okay, I know the value of the function. And this is called the decision tree because we can arrange it in a tree-like fashion where each node is labeled with the variable you query at that step, and the edges are labeled 0 and 1 based on what you see. So in this model, the decision tree complexity of a function is the number of queries you need, which is the depth of the corresponding decision tree. And clearly, decision tree complexity will never be more than n, since you can just ask about all the successive values of the variables, and once you have all of them in your hand, you know the value of the function. But it turns out for some very basic functions like OR, this n is tight. So OR is a pretty easy example. If you keep asking about variables in any order and you keep seeing 0, then you have to keep asking because you never know what the value of the function is until you've checked every bit. So that's why we call it a weak model. Now let's look at our stronger model, communication complexity. So in communication complexity, we're not going to be dealing with one set of variables, the z variables, but we're going to be dealing with two sets of variables, the x variables and the y variables. And we're going to take each of those types and we're going to give them to a different person. So Alice is going to get the x variables and Bob is going to get the y variables. And what they do with the variables on their own sides, we're not going to put any restrictions on it. If they want to solve the halting problem or figure out whether the Riemann hypothesis is true or false, that's their prerogative. But of course, if they want to solve f, they can't do it in isolation because the other player has the other side of the input. And so they're going to need to talk to each other in order to solve the function. And we're going to charge them for each round that they talk to one another. So this is going to be communication complexity. And again, we can arrange this in a tree where at each node, instead of querying one variable, Alice or Bob, whoever's turn it is to speak, is going to compute an arbitrary function over the inputs that they have and based on the path in the tree thus far. And then again, we'll have edges labeled 0 and 1. So once again, the communication complexity will be the depth of this tree corresponding to the maximum number of bits sent. And well, for some easy functions like OR, now communication complexity does very well. If we just give half the variables, if we give some of the variables to Alice and some to Bob, either one of them can just report what the OR of their variables are, and the other one will know the answer. So this is maybe not great motivation for why communication is a strong model. Let's see some more convincing evidence. So if we go back to one-party functions, f over z1 to zn, we can define a two-party function called the search problem, the canonical search problem, where Alice is going to get an input to f that forces f to output 1, and Bob is going to get an input to f that forces f to output 0. And since they give different outputs, they clearly can't be the same input, and so they must differ in at least one of their bits. And their only job is to find a bit where they differ. So this seems like a nice little search problem, and you could ask how hard this thing is. And the answer, via Karshmer and Vigderson, is that it's exactly the formula complexity of your original function f. And by exactly, I mean you get the same tree with the same labels at the leaves. The characterization is really tight. And if you know anything about formulas, you know that proving lower bounds on the depth of formulas is a really, really hard problem. Right now, the best we've got is order log n, and not a very big order log n. So if we could get stronger lower bounds via communication complexity, this would be major progress on one of the long-standing open problems in circuit complexity. So a reasonably strong model. Now, what's the connection between these models besides having this tree-like structure? Well, what we have on one hand is a model that's so weak we can get lower bounds for it on basic functions. So that's not too interesting. And on the other hand, we've got a model that's strong enough to, where lower bounds elude us and where we really want to prove stronger and stronger lower bounds. And it would be nice if we had some way of taking the lower bounds against the weaker model and transforming the function in such a way that we could get lower bounds against the stronger model. So this seems like a lot to ask for when there are such huge gaps between the complexities of the two functions. But we're going to see some intuition for why this could be the case from some of the lower bounds we do have for communication. One of the first lower bounds anyone learns when they take a communication complexity course is on disjointness. So in disjointness, Alice and Bob are each going to get a set over the universe of size n, given to them as a incidence vector. And they want to output 1 if and only if there is some element that's in both of their sets. So what connection does this have to the OR function? Well, in the OR function, we've got n bits, and we want to check if any of them is 1. And in disjointness, we have n elements, and we want to check if any of them is an overlap point. So if we just look at them in logical form, disjointness becomes the same as the OR function, but we replace each of our original variables, zi, with a little and over one of Alice's bits, xi, and one of Bob's bits, yi. And the lower bound on disjointness, the full linear lower bound, tells us that Alice and Bob can't do that much better than doing whatever the decision tree for OR did, namely querying the bits 1 in a row, and communicating in order to find out the value of the variable that they're querying at any given time. So somehow the AND has obfuscated each of these ZI variables such that we can no longer express these really interesting, complicated relationships over the ZI variables in one step. We really have to focus on one ZI and solve it in order to know anything about the top function, at which point we're kind of pigeonholed into, or the communication protocol is pigeonholed into just following, say, a decision tree type model. So more generally, this gives us the idea of gadget lifting. And gadget lifting is exactly where we take a one-party function and turn it into a two-party function by replacing each variable with an inner function g, which we call the gadget, applied to some fresh set of variables. So zi will be replaced by g of xi, yi. And again, we want to pick this gadget g such that if Alice and Bob want to know anything about zi, they're basically going to have to solve g. And in particular, since these inputs are disjoint, we're going to hope that they basically have to solve the g's one at a time. So some natural examples that might help us if we're trying to obfuscate things maximally would be like the parity function, right? So g is xi parity yi. And we're going to see an even more general gadget, which is called the index gadget. So the index gadget is going to have some parameter m, and I'm not going to tell you what m is just yet, but fix some m, and then Alice is going to get log m bits, which we're going to interpret as a number from 1 up to m. And Bob is going to get m bits, which we're going to interpret as a Boolean array of length m. And the value of the index gadget is simply going to be what the value in Bob's array is at the location pointed to by Alice's element. Why I'm calling this general is because we could also think of this as Alice getting the input to a log m bit function and Bob having the truth table of that function. And so, we can capture parity or and or anything else as long as we're willing to let Bob have a much larger gadget on his side. And it turns out that this is general and obfuscating enough to work. So the grandfather of all lifting theorems is Raz and Mackenzie from 1999, which was reinterpreted in 2015 by Goose, Pitassi, and Watson in this lifting language. And what this result shows is that if you pick m big enough, like a polynomial in n, then the communication complexity of the lifted function is the decision tree complexity of the unlifted function times a log m factor. And the log m factor is what it takes to solve the index gadget. So to see the easy direction, if we have a decision tree of depth d solving the unlifted function, then Alice and Bob can just mimic it by starting at the top, and whenever they need to query a variable zi, Alice sends over all of xi, and Bob sends the value of the index gadget, because he now knows where the pointer is. So in this way, they can get a communication protocol of depth d times log m plus 1. And the other direction is going to be the harder one, and that's what we're going to talk about today. But first, I need to justify why I'm here. This is a 20-year-old result that has already been reproven once. So what are we adding to the table? What we're adding is an application of sunflowers, a combinatorial object, in a central part of the proof. And we do this for three reasons. The first is that this works for not just this basic tree-like lifting theorem that I've introduced, but also a number of other lifting theorems that we care about, such as the associated DAG-like version, a version where M is made to depend on the depth of the protocols rather than N itself. And there are many other lifting theorems that we care about. And for these three in particular, and quite possibly, quite likely many others, this sunflower technique we introduced goes through. And this is interesting because all these proofs actually used different arguments at one central part of the proof. They had some framing which was very similar between the different proofs, and then they had this central lemma that they proved in somewhat different ways. And our proof covers all of those. And not only does it cover all of those, but it drastically simplifies them. We're going to have a lemma, which is from combinatorics, which is used in sunflowers. And that lemma plus maybe half a page is going to do most of the heavy lifting that took pages and pages in previous proofs. So this is a really nice simplification. And besides these two qualitative improvements, we do have a quantitative improvement, which is that once you replace this centerpiece of the proof with our sunflower technique, your gadget size drops. Now, when you go to apply lifting theorems, the size of your gadget is going to play directly into your lower bound. And the larger your gadget, the worse your lower bounds are going to be. So getting M to be as small as possible, maybe one day order 1, is very important. And previous proofs of lifting had anywhere from n squared, which took a lot of work to get for the tree-like case, all the way up to n to the 256, which is still as good as it gets for some of these proofs. And when you replace the old proofs with the sunflower proof, all of the proofs drop all the way down to almost linear. So n to the 1 plus epsilon for any choice of epsilon, or even n log n if you're willing to sacrifice a bit in your lower bound. And more importantly, this gadget size is now directly tied to the sunflower lemma. We've removed all dependence on the gadget size everywhere except for in this application of sunflowers, meaning that if we can get further improvements to the sunflower lemma, something that's been a very active body of research in the past 3 or 4 years, then you're going to get better lifting theorems as an immediate consequence. So this seems like the most likely way forward in the current state of affairs for getting smaller gadgets. All right, so that was the preamble, and for the rest of the time, I want to describe at a high level how you prove these lifting theorems. This is going to cover basically all the previous proofs, and then with our new sunflower change. So hopefully when this is over, you have an idea of how all of these proofs operate to some degree. So we're proving the hard direction, which is that we have a communication protocol, which has depth d log m for the lifted function, and we're going to extract from it a decision tree for the original unlifted function f of height only order d. And to do this, I'm going to have to give you one more view of how communication protocols operate. And if you haven't seen this before, this is the one to remember. If you take communication complexity, this is the one that's most useful. So in a one-party function, the natural description is a truth table. And a truth table is just a vector of length 2 to the n, where each entry is indexed by an input to the function, and the corresponding value in the vector is the value of the function. Well, if you move to a two-party function, then you could just look at this as a matrix instead, where the rows have Alice's side of the input and the columns have Bob's side of the input. And again, on entry x, y, we put the value of the function f on inputs x and y. So the useful thing about this is that if we go back to communication, let's say Alice speaks first. Well, we're letting Alice and Bob agree on any protocol they want, and computationally unbounded and such. And so really what Alice is doing in the first step is she's saying which side of a pre-agreed upon partition she's on. So they split all of Alice's potential inputs into two groups, and Alice says which group she's in. And if we look at rectangles, this just corresponds to partitioning the communication matrix in half. And once they do this, and she reports which side of the partition she's on, they can actually just toss out the other half, since they've asserted that they're not in that part of the communication matrix. And next, say Bob speaks, and once again, there's a pre-agreed upon partition, and he says which side he's on, they toss out the other side, and they keep going. And once you get to the leaves, well, it had better be the case that they know the value of the function, which means it had better be the case that whatever rectangle is left over has all the same entry everywhere. And we call this a monochromatic rectangle. So this is another view of communication protocols, which is particularly useful. All right, so keep that in mind. We'll come back to it in a second. But for now, we're going to get into the intuition behind the proof. So for starters, the whole reason we're doing this gadget lifting thing is that our gadget should be obfuscating the variable zi. And what we mean by that is that Alice and Bob need to work in order to get at any particular input to the unlifted function. And we're going to say that a coordinate is important if it looks like they're spending a lot of communication trying to figure out the value of a variable. In particular, if they spent something like order log m bits of communication trying to learn about a particular zi, then first of all, this seems like a coordinate that we should know about, and so it's worth querying in the decision tree. And second of all, they've spent order log m bits talking about it. And our goal is to shave a log m factor off of the height of the communication protocol. So we're happy to query the variable zi, and we're keeping pace with what the communication protocol has done thus far. And what's important is that if we commit to this view of what an important coordinate is, then the index gadget had better be doing its job for the rest of the coordinates. In other words, if they haven't spent something like order log m bits talking about the variable zi, then they had better know nothing about it. And remember, since the lifted function is really f on the outputs of the gadget, these coordinates shouldn't be able to influence the output of f if they're completely free. So this is going to be the dichotomy that we're going to keep in mind as we decide how to do our decision tree. Now, Alice and Bob aren't going to declare what kind of information they're sending about the variable zi. They can send the parity of all of their bits. And now they're talking about a little bit about every different coordinate. So we need some way of knowing how much information they've actually sent about a coordinate zi. And here's where our rectangle view comes in handy. We're going to say that the amount that they know about zi depends on the x side of the current rectangle. So if we're at RV, it's going to depend on the x side, xv, when you restrict to the coordinate I. And we're going to ignore y. We're not going to talk a lot about y in this talk. Intuitively, Bob's input is so big that it would be really, it's a waste of their time to send bits that they aren't sure about. And bits that they're sure about mean that Alice has sent a lot of information about her pointer. So again, it's worth focusing on Alice's side. All right, so more precisely, we're going to quantify how much we know about the ith variable by the entropy of the x set when you restrict to I. So if we fix a particular assignment, then inside the brackets here, we have the typical entropy expression for that particular assignment. And we're going to care about the min entropy, which is that we look over all coordinates I and all assignments to the possible assignments to those coordinates alpha I. And we're going to minimize the entropy over all those. Now, entropy, if you haven't seen it before, it roughly says how many bits are still left indeterminate. So in particular, if there's some coordinate I for which we know exactly what the value is in the ith coordinate, in other words, there's some alpha such that x sub I, x is alpha in the ith coordinate for all x in capital X, then our min entropy is going to be 0. And meanwhile, if no matter which coordinate you pick and which assignment you pick, you're basically uniform, then our min entropy is going to be like log m. Again, this is like 0 bits have been taken off of the full log m possibilities for Alice's side. And this intuition about it's how many bits have been are still unrevealed carries over really well in our rectangle model. If you have a rectangle RV and you partition it in half, say along Alice's side, then what you get is that whichever side is bigger actually loses at most 1 bit of min entropy. The min entropy of the smaller rectangle, or of the larger rectangle but in the partition, is at least the original min entropy minus 1. And this is great because this means that it takes you something like omega log m rounds before your min entropy falls below, say, 1 minus order 1, falls by an order 1 times log m factor. And in particular, there's going to be some coordinate I and some assignment alpha I that witnesses the fact that your min entropy is less than this threshold. And this tells you exactly which variable to query in the decision tree. We're going to query zi, and we're going to be happy knowing that it actually had to spend all of those rounds dropping the min entropy in that coordinate. So now we want to make sure that whatever rectangle we're maintaining actually does agree with everything we've queried in the decision tree so far. So if our whole rectangle from the communication protocol is RV, and we've got this 2 likely assignment, xi equals alpha, well, we're going to toss out every x that doesn't agree with that 2 likely assignment first. And then we're going to split up on the y side, we're going to split things up between the y's that give 0 on the index gadget in the ith coordinate and the ones that give 1. Remember that we're fixing one particular value for the ith coordinate on Alice's side. And then when we query it in the decision tree, we're just going to throw out the wrong answer. So if we query the ith variable and get 1, we're going to only keep the part where the index gadget outputs 1. And if we get a 0, then we're going to only keep the part where the index gadget is 0. So that's what's happening in the important coordinates. And we need a central lemma to take care of the unimportant coordinates. And what it's going to say is that as long as you, so we're going to let J be the set of coordinates that we fixed so far. So bar J is going to be all the free coordinates. And our central lemma says that if the min entropy of X is high on the unfixed coordinates over line J, and Y itself stays relatively large, then the index gadget has all possibilities available to it. And this isn't just that any unfixed coordinate has both 0 and 1, but rather all joint assignments to all of the unfixed coordinates are still available to us. And so then our central subroutine is going to be that we have the rectangle RV associated with the node V in the communication protocol. And then we're going to be maintaining our own rectangle inside of it. And that rectangle is going to have all the nice properties we want. For the coordinates that we've fixed, every entry in R is going to agree with the value we've fixed in the decision tree. So whatever the decision tree says that Zi should be, our rectangle is going to agree with that. And then outside those fixed coordinates, the min entropy of the X side is as high as we need it to be. It's like 0.95 log n. And that's going to be for our central lemma. And there's this condition that Y stays large, but we won't get into that today. So this is going to be our main invariant. And again, since the communication protocol has to spend log m bits making a coordinate important enough to query, then after d log m rounds, we will have queried at most d coordinates in our decision tree. And so then the last thing to do is prove our central lemma. And this is going to be the more formal version, which is that if the min entropy of X is at least 0.95 log m minus order 1, we'll give it that flex. And the Y side starts off as size 2 to the mn, because there's Bob is going to get n bit strings of length m. Our largeness condition on Y is going to be that we have at least a 2 to the minus n log m fraction of our original size. So if these two conditions hold, then not only is the full output range of the index gadget available, but there's some special row X star in capital X, so that even if we tossed out everything except for X star, we'd still have everything available to us. So this is actually overkill for proving the central lemma, but it has the advantage that it's not overkill for other proofs like DAG-like lifting. And so this is going to be the form that we want to prove, and it actually is the form that follows more directly from the sunflower lemma. And with that, it is finally time to introduce sunflowers. So sunflowers are an object in combinatorics that appear all over computer science. Anup Rao actually just recently wrote a nice survey about many of the places where sunflowers appear. And what a sunflower is it's a set system, so it's a collection of sets, such that there's some special set called the core, C, where all the sets intersect. In particular, if you picked any two sets in your set system, they would only overlap in this core. They would both contain the core and they would have no other overlap. So pictorially, it should be fairly clear why we call this a sunflower. So these were introduced in the 60s by Erdős and Rado. And what they cared about was certifying that a larger set system has a sunflower inside of it. They showed that if all of your sets have size at most d, and your whole set system has size at least d factorial times k to the d, in other words, if it's sufficiently large, then there is a sunflower inside it, and that sunflower has k sets in it. So you can pick k to be whatever you want, and as long as your set system is appropriately large, you can find a sunflower of that size in there. And follow-up work on the sunflower lemma has focused on improving the requirements on the size of your set system. So the ultimate goal is to remove any dependence from D on D from the base. And our first real improvement, like substantive improvement in about 60 years was this result by Always et al., who showed that the base can be reduced to k log dk. This was a huge result, and I hope that there's a lot of follow-up work that comes out in the next few years. Sunflowers really deserve quite a bit of more attention than they even currently get. But while we're not going to go into the always at all proof, we're going to isolate this one lemma, which says that translated to our language, if F has sufficiently large blockwise min entropy, where sufficiently large is basically log n over epsilon for a universe of size n, then if you pick a random set of the whole universe, the probability that that set doesn't contain any of the sets in your set system F is at most the epsilon that you chose. So this relates to sunflowers because this is connected to an approximate notion of sunflowers, but we're going to use this lemma straight out of the box. And from here, our proof is pretty straightforward. So we're going to assume for contradiction that there's no special x star that gives the full range of the index gadget. And so in particular, for any x you pick, there's a bad assignment beta x, which is not in the output of the index gadget when you restrict to x. And the worst case is going to turn out to be when beta x is the all ones assignment. You'll have to read the paper to understand what I mean by worst case. And we're going to now transition to a set view of x and y. So our universe is going to be Mn, and x, each x in capital X is going to be a set of size n. Remember that there are n coordinates in x, and each of them is a pointer from 1 to m. So this defines a set in Mn of size n in the natural way. And our blockwise min entropy condition on capital X, we're going to assert that this actually is good enough for the sunflower lemma that we were using. So in particular, we're going to pick epsilon to be 2 to the minus n log m. And we want that our blockwise min entropy is at least like roughly log mn over epsilon. Mn is the size of our universe, remember. And I want to point out here that this is the one place where we have to fix the gadget size. So we need, for this condition to hold, we're going to need to pick m to be something like n to the 1.1. And it's pretty clear since we picked 0.95 arbitrarily, you can make this n to the 1 plus epsilon by adjusting the parameters accordingly. So anyway, once we fix m to be sufficiently large, then we have the conditions for our sunflower lemma. And so we know that if you pick a random set over the universe Mn, the probability that none of our sets X is contained in this random set is at most the epsilon we picked, 2 to the minus n log m. And just moving to an incidence vector view of these things, if you pick a random bit string of length Mn, and we view it as a set where the ones are the elements included, then it says that for any x you pick, the probability that that y does not equal the all ones vector when you restrict to the spots indicated by x. The probability that that doesn't hold for all x is at most epsilon as well. This is the same line moved up. And now if we just look at this as the set of vectors fulfilling this condition, we know that that set has size at most 2 to the mn is all possibilities minus n log m, which is less than the size of y. And what this means is that there's some y in capital Y which doesn't fulfill these conditions. And you can show very straightforwardly then that it means that the index gadget actually does output the assignment that we claimed wasn't there, even restricted to little x. So this is the end of the proof of our main lemma and the end of our lifting theorem. So before I go, I just want to mention a couple things to think about going forward. The first is that while we're the first ones to show that better sunflowers imply better lifting, there's actually already a result that shows that better lifting implies better sunflowers. And so it'd be nice now that we have this bidirectional implication to develop kind of more a deeper connection between sunflowers and lifting, maybe some syntactic equivalence between them instead of just proving these two separate directions. And then for more straightforward open problems, the main one, of course, is to reduce the gadget size further. So we have n to the 1 plus epsilon. It would be good to get it to n. It would be good to get it sublinear. And it would be fantastic to get it a constant size. This would have many, many implications throughout complexity theory. And if you think that this might be a little tricky, a little too tricky, then I would suggest looking at other gadgets besides the index gadget. So the inner product gadget is one that's been studied quite a bit, but for which we only know some of the results that we know for index gadget. And if you can make our proof technique work in the for the inner product gadget, say, then this would imply immediately the rest of the lifting theorems that we care about, and that would have further implications as well. So that's it, and I just want to make a quick plug, which is if you want a more technical, in-depth version of this talk, it's recorded on YouTube for the Meow Research Seminar, so I suggest you check that out. Or, of course, feel free to read the paper. But anyway, that's it. Thank you so much, and I will see you at the virtual session.